As you can tell from the title of the lesson, the Fundamental Theorem of Calculus is probably pretty important. We obviously can't continue through the entire year drawing geometric shapes to find the area under curves, because what if we had something like a parabola, for instance? We don't know how to find the area under the curve for that. We can do it okay with triangles and trapezoids and rectangles and circles and semicircles and that kind of fun stuff. But we need to eventually get to something where we can do some meaty calculations. And this thing that we're going to do today is the Fundamental Theorem of Calculus. There's actually two parts to it. Today we're going to do the first part. On Monday when we come back, we'll do the second part. So today is all mechanical. Next Monday is all theoretical. So you're going to have to evaluate the definite integral using the Fundamental Theorem of Calculus. You're going to have to understand the mean value theorem for integrals. So we had a mean value theorem for derivatives, which was what?
The slope.
Algebra slope.
Algebra slope equals calculus slope. It's completely different here. We'll talk about an average value of a function. That'll be fun. And then we're going to talk about the second fundamental theorem of calculus. Again, that's a week from today. And then, of course, your tip for today is to meet somebody new. Just stop a stranger in the hallway, introduce yourself. That wouldn't be too awkward. Okay, here it is. The fundamental theorem of calculus. We want to be able to calculate a definite integral. So we know this notation already. This is a function f of x. We're going from a to b. And we want to be able to calculate the numerical value. So what we've done now is we've drawn geometric pictures. But this is the process that we're going to go through. Just so we understand what's going on here, what is capital F mean? If we start with f of x, what is capital F?
The integral.
The integral, correct. The antiderivative of f of x. So in simplistic terms, what this means is we're going to find the antiderivative, we're going to plug in b, we're going to plug in a, and then we're going to subtract the two. And that'll give us the area under the curve. Question?
You said 4/4 is on the quiz tomorrow.
Correct.
4 is on the question?
Is not up through 4-3. 4-1, 2, 4-3. So all we're going to do today then is practice this, because this is comparable to the power rule in derivatives. It's the basic process for taking integrals. And then, of course, it'll get a little bit more complicated when the functions don't play so nice. But up until that point, this is our fundamental theorem of calculus. Okay. So I made the color change, found the button in PowerPoint that allows you to change the color. But, yeah, feeling a little crazy. I threw it in there. Nice. Goes from red to blue. You know,
Or green.
no, the green wasn't an option.
Ooh.
Okay, so we've done this already. You should be able to take the antiderivative of x cubed. Peter, what's the antiderivative of x cubed?
1/3 x.
You faded off there at the end.
No, it's on the, it's on the,
1/3
mine's 11.
x.
Don't point at him.
1/4.
You can do it.
I can do it too.
Mondays are rough.
I understand.
I have to redeem myself.
It's 1/3 x to the 4th, right?
Not quite. You got half right.
1/3 x to the 3rd.
Jesus, why can't I do this?
Would you like some help?
Yes.
Grant?
1/4 x to the 4th plus C.
No plus c. Definite integral.
I told you, Tyler.
1/4 x to the 4th. So we're not going to spend a lot of time doing the antiderivatives because theoretically you should know how to do that. What we're going to do is practice the fundamental theorem of calculus.
Why are we plus b?
Because it's a definite integral, we'll get a numerical value. So it's not a family of solutions. So here's how the notation goes. You take the antiderivative 1/4 x to the 4th, then you draw a line. That's actually a segment. And you put 0 to 3. Okay, so that means I've taken the antiderivative, but I haven't plugged in my numbers yet. Now plug in the numbers. 1/4 3 to the 4th minus 1/4 0 to the 4th. So you plug in the bigger number first because it's f of b comma f of a. Anybody know what 3 to the 4th is?
81.
81 divided by 4 is 81/4 minus, what's 0 to the 4th? Good, times 1/4, 0, and sure enough, we get 81/4.
Good job, Tom.
That we could not have done with the geometric stuff that we talked about because it's a cubic function. It's got, you know what a cubic looks like. You're all fairly bright. You know, we're not going to get a nice geometric figure there going from 0 to 3. We get that little curvy thing. We could approximate it with rectangles, but again, the Riemann sums and rectangles were approximations. This is the exact area under the curve now. So we're done with approximations. Pretty easy?
Yeah.
Good. Let's try some more. Question before I erase? See.
It's all about this. Well, is there a quiz tomorrow on day 66?
It's on paper.
It's
It's on paper.
encouraging.
Yes.
I'm sorry, what?
It's not on what we did for 60 and 61.
It is.
But it says only through 4.2.
I know, but as I mentioned on Monday, there's a typo on the assignment sheet.
Wasn't here Friday.
Oh, well, now you know.
Thanks.
No problem. So there's the work again. I had already typed it out, but if you want to write it as I like 1/4 x to the 4th, but you can also write it as x to the 4th over 4. It's the same thing. Sometimes this gets confusing when you have fractional exponents because if it's, let's say, 2/3 and you do 2/3 plus 1 is 5/3 and then you multiply by the reciprocal, but then you divide by it and then you have, you know, all right. Anyways, try that one on your own. Might want to start by rewriting it. Anybody want some gum?
I have some, thank you.
I got some too. Now on my shoe if you want it. It's pretty chewed. Excuse me. Sorry. Should eat breakfast. Who's got an answer?
Wait. I almost got it.
Oh, go put that up there. It won't hurt you, just go up there. Coward. Click on the top button so you're in the pen mode.
What did you get?
Then pick a color.
Ew.
I wouldn't recommend
Oh,
green.
can I have-
Okay, that's solid. Now,
Oh my gosh.
do what you gotta do.
It's solar from that.
Yeah, it's like $7.
That's awesome.
Even though I noticed your like it was just
Oh,
just
use
use
your
your
tongue.
I didn't go to the
My
So you get a lot of Milky Way.
Oh wait. Thank you.
coming.
What did he say?
Because Tommy's wearing a.
Making
I know, but like,
galaxy
what did he
jokes.
say?
He said, "Did you go trick or treating this year?" And Tom was like, "No." Also, you didn't get that many Milky Ways.
I hate my life.
Yay!
Well
My
done.
hands feel better. Thank
Let's,
you.
we don't want to assume too much because you know what happens when you assume things.
You
But
make it-
how do you do 4 to the 3/2 power?
4 to the 3rd.
You have two options.
You can make it like 2 to the
One option would be
2 to the 2.
calculate. Okay, 3 options. One is the calculator. Second option,
Your brain.
Well, the brain would be the overseeing category for the other two subcategories, so I would have to give you half credit on that one, Maggie, thank you.
Oh, you can make it 2 to the second power and then cross that. Like,
Is this recording? I don't think this is recording.
Yeah. Unfortunately, it is.
you raise it.
The brain.
Okay, so what, again, how do you do 4 to the 3 halves?
To raise it to the third.
Yeah, you can either take 4 to the 1/2 power, which is 2, and then cube that, or you could take 4 and cube it, and then take the the square root of that. I would recommend doing the square root first, because the numbers stay smaller. Does anybody know what 4 cubed is?
64.
It's 64, right? If it's a manageable number, that's not too bad. And 1 to the 3 halves would be 1. Good.
What?
So that's 8 times 2 is 16 minus 2 is 14. Well done, Olivia. Nice job.
And then times 2 is 16. And then subtract.
Looks nice.
I got the same thing. Good job.
Yeah, I do.
Okay, and
So much.
let's be careful on the notation here. As soon as you take the antiderivative of the function, the squiggly mark goes away. Don't continue to write the squiggly mark until the end because it makes no sense. It's just like the derivatives. Once you take that derivative, or a better analogy would be the limits. Once you take the limit, you're done writing limit over and over again. Same thing is true here. Okay. How about that one?
Oh, yeah, no.
You knew some trig was coming.
I still don't know what that is.
Those on you. I have it written down
Yeah, I'm gonna go find it.
somewhere.
Not only do you have to be able to do the antiderivative, then you have to be able to plug in pi over 4 and 0 into it.
Oh, it's easy.
Wait.
Once I learn how to do it.
Where is secant family, right?
I don't remember. Sorry, Tyler, I can't help you there. I never learned
I don't
that.
know, I'm just gonna make it up.
I'm just going to make it up. Famous last words. Yes, sir. Yeah.
Alright, so pi over
But it's
4.
not
Raise the exponent by 1. So 1/2 plus 1 is
What?
3 halves.
What's
And then multiply by the reciprocal of that number.
It's
Multiply by 2/3, but the 3 cancels with 3.
Yeah, but then you
2/3
have
cancel with 3 as well.
incredible.
Okay, well, I'm still plugging in because I don't like trig at all.
What if you just?
I don't remember, I'm sorry. I forgot. You'll show me.
Oh, yeah, it's.
Because I'm writing this red, I don't like.
Front face. See, wow.
Oh wow, that's insanely easy and I feel bad for
That's what I'm
starting
trying
with
to
this problem. Okay.
What's your question? Because that says I took the antiderivative. That's zero back.
So wouldn't it be?
Because because 0 and 0 cosine is no 1.
Second
Because cosine is the x value.
I don't know if it's actually effective.
Oh, we just go 1, 2, 3,
I was
4.
flipping
Yeah.
through the channels last night. There there's like words going on. Right, there's bang bang. I was watching
Tommy, can we also, are you up on nebulas? Because I got a couple more brewing, but it requires a little bit of nebula now.
You have to explain
So they're not as bad.
Okay, so I'll just throw it out there, you know, when the time is right, I'll throw it out there, and if you get it great, if not.
Someone taking you again.
What do you want me to say?
I'm down.
Yeah, I'll give you the number.
Like some.
Okay, what do we got?
1!
1? 1?
Yeah.
Why?
Because the integral of secant squared is tangent.
Did you turn 1 into Juan?
We just did it at the same time.
1. Good. So secant squared is tangent. Put the bar in there because I haven't plugged it in yet. Remember, you plug in b first, then subtract a from it. So 1 minus 0 is 1. Okay? Pretty easy? Yes? Okay. Now, the biggest mistake that people make is not taking the antiderivative correctly. It's screwing up on the notation. Not getting rid of the squiggly symbol when they're supposed to. Not drawing the bar in there so you know what to plug in. Or sticking plus c's on the end of this. Okay, this isn't 1 plus c. The plus c's are only for indefinite integrals. We're doing definite integrals. Okay. How about that guy?
Oh,
Whoa!
no, this is
This is gonna be tricky, cause you don't know how to do an absolute value.
Oh, so that's what,
oh, it's absolute.
The absolute value.
Way worse.
It does make it way worse. But if you're sneaky about it, you can do it.
You just take out the absolute value.
There you go.
Divide everything by absolute value.
Just change the rules.
Divide everything by absolute value and you're good.
What's this notation? I'm dividing by the double absolute value bar. Isn't that legal?
You plug y in for x squared minus 2x minus 3, and then you just divide by the inverse of the absolute value of y.
This will act as a nice review for us because I think some of you may have forgotten. What does the absolute value do to a function?
Puts everything above the x-axis.
Puts everything above the x-axis. So that tells us at least we should get a positive answer because everything will be above the x-axis. But how do I solve this problem? Well, first things first, I would pull out the calculator and graph that function, not with the absolute value. You can graph it with the absolute value if you'd like, but just graph the parabola and see what it looks like. If you're feeling saucy, however, in y1, put in the absolute value thing, and then you'll get a good picture of that W-looking thing. And figure out how we're going to find the area of that bad boy. Catalog. It's the first choice in catalog. You know what a catalog is?
Or you can go to math and then num.
New.
New or not? I don't know if there's a correct pronunciation.
I was just, I had
Or
no,
equal.
I should know my you.
Catalog.
Oh,
That was really Oh, that's awesome.
Okay, we got a graph? How we're gonna find the area under the curve of that thing from -2 to 3. So there's the graph. I wanna know the area under the curve from -2 all the way over to 1, 2, 3, there. How do I do that?
Take the area of a semicircle.
It's not a semicircle, it's a parabola. Pat, are you mumbling? What are you saying?
I don't know, maybe keep the absolute value thing in for the whole thing.
Do you know how to take the antiderivative of an absolute value?
No, I'm just gonna do
No,
the
I
middle,
don't either.
I'm just gonna do the middle and slap them on there.
So just take whatever you get for an answer, put absolute value around it, and call it a day.
That's what I'm doing.
You get 6, or the absolute value, I got 6. You get -12, it's 12.
I'm saying like after you take the antiderivative of what's in the middle, then you put the absolute value. Is that not?
Say that again?
You take the antiderivative of what's in the absolute value,
Uh-huh.
and then you just take the absolute value of that. And
That's not a horrible idea. You're on the right track.
Don't get stuck on.
Can you get like A or B?
What's that, Jake?
Don't you, after you take the antiderivative, you put the line, or is that
No, there's more than that.
a segment?
It's a little more complicated.
A little more complicated?
Plus c.
We know that.
I mean, we like looked at
We know that's not right.
Okay, let's do this. If I forget about this curvy part that got flipped over, if I just look up to this point, can you find the area under the curve from here to here?
Yeah.
Yes.
Yeah? How?
What?
No, it's not a triangle actually. That
It's
thing curves.
got a little.
It's got a little curve to it.
You do what
Yeah, the
Drew
right.
did previously.
I'm sorry?
You do the same thing, but from what is -2 to -1
Of what?
of that same equation.
But what equation? The whole thing? Or just what's inside?
Just
With or
what's-
without? Just with
Without the absolute value.
this?
Yes,
Why?
because it's the same points.
Everybody okay with that?
Yeah.
If there was no absolute value bars, the function up until -1 looks like it normally would, because you'd have this parabola going down here and everything would be peachy keen. So from -2 to -1, it's the regular function. And one of the things that we can do is we can split a function over an interval from -2 to 3 into two different intervals. And this is when we were introducing the property, we said, well, if I go from 0 to 10, instead of going from 0 to 10, I could go from 0 to 7 and from 7 to 10, and it seemed like a silly thing. Well, here's an application of it now. That takes care of this part of the graph. How do I get that part of the graph then, using an integral?
3 on top and maybe 1 below.
Okay. Now what am I taking the antiderivative of?
The regular equation.
This?
Yeah. Or
With a negative in front.
I'm sorry? You don't like this?
Is it plus 3 and plus 2x?
oh, shouldn't it be plus the 3 to 4?
With a negative in front because it's flipped.
Nice. There you go.
Um,
Explain that again, because I heard her ask already.
Because that is flipped upside down from the original equation, we just put a negative in front of the entire equation.
Does that make sense?
Yeah.
The original function, just the parabola, looks something like this. From here to here, if you look at this graph to this graph, from -2 to -1, nothing changed. It's the same graph. So we can just use this. The problem is, from -1 to 3, things are all screwed up. In the original function, it's below the x-axis. We don't want it below the x-axis. We want it above the x-axis. So if I use this from the original function, I'm going to get a negative answer for this area under here. Is everybody with me? So if it, hold on, let me finish my statement. So if that's a negative area, I don't want it to be a negative area because it's above the x-axis. So by putting a minus sign in front of it, it flips it into a positive area, and so we get a nice, pretty answer there. Emma.
How do you know that it goes from -2, or I get the -2 part, but how do you know that it like changes at -1 just from graphing it?
Yeah. Or you could solve for zeros, but I mean, graphing it is what told me where it hits. All right. And you could, if you don't want to put the minus sign there, you can turn it into minus, but I like to leave it in there because it indicates exactly what I did. I took that area that in the original function would be below the x-axis and flip it up into the top portion to make it a positive area. That doesn't happen very often, but again, it's another way that we can find the antiderivative of an absolute value without actually doing the math to find the antiderivative of an absolute value. The other way was when we talked about graphing it and you get the v. That's not a v, that's just a function that flips part of it up into the positive regions. Okay? Okay. One of the things that we're going to talk about, or one of the pieces of terminology that I'll use a lot, is thinking about the integral as an accumulator. By that I mean, when we start to find the area under a curve, so let's take some plain old function. Let's do this, and we're going to go from here to here, and so this is -3, and this is 3, and that's 5, so that's the integral from -3 to 3, of, what is that function? -x squared plus 5. My x went a little wonky there, sorry.
Plus the
Okay. What we're doing is, the integral symbol is actually an accumulate. What does it mean to accumulate? Add up, right. So it's taking and calculating little skinny pieces of area. And if I continue to add these little pieces of area as I move to the right, eventually what happens is I end up filling in the whole thing. So we're going to get these little slivers of area. Right now in your basic calculations, those little slivers of area aren't that important, but for the stuff that we're going to do in the future, that concept is very important. So this squiggly mark says I'm going to start at -3 and I'm going to start accumulating little bitty rectangles from -3 all the way to 3. How big are those rectangles, by the way? How thick are they?
0.
0, correct. They have no width. And so I'm actually going to end up generating an infinite number of rectangles as I move from -3 to 3. And then that keeps accumulating those areas, which makes no sense really. How can we accumulate the area of rectangles that have no area? It's a little theoretical, but you get the idea. Right. For this stuff, we're not going to use it that much in the basic mechanics that we started in this section, but later on when we start doing all kinds of crazy things like spinning shapes around axes and calculating volume and all these other fun stuff, that's going to become fairly relevant. And then the other thing is displacement versus total distance. So when we talked about taking the antiderivative of velocity to get the position function, without the absolute value bars, it's the displacement. With the absolute value bars, it's the total distance. Do you understand the difference? It's a simple yes or no.
Yes.
Yeah. Does anybody not? Because I'll demonstrate. Okay, displacement is the distance from where you start to where you end. Okay, so for instance, if I start right here, and I walk forward, and then I back up, and then I move forward, and now I'm cha-chaing, and then I go back, and then I move forward, and then I back up, and I stop here. What's my displacement? Zero. Okay, what's my total distance? Is that also zero? No, because I covered a whole bunch of distance in there when I was doing the cha-cha. Okay. This is a simple thing that will save you a lot of hassles if you can remember it. Because instead of having to calculate each individual step, I'm not going to calculate how far I went from there to there and then subtract backing up and then adding going forward and then subtract backing up and all that. I can just do a displacement and get back to zero. If I want to find total distance, just throw an absolute value around it, and that'll give me the total distance that I traveled. Okay, we good? Next thing that you're going to love. If your calculator is updated, so pull out your calculators. Some of you might have your calculators updated, some of you may not. If it's not updated, this is the point in time where you're going to want to get yours updated. So go under math. Can I use yours for a second? Because I don't remember the keystroke. Okay, so math down to 9 is fn int. Hit enter. Now, real quick, when you hit enter, one of two things happens. It puts fn into the home screen, or it draws a little squiggly. How many have squigglies? Okay, for those of you that don't have squigglies, we need to update your calculator. Okay, if you have an 84 or an 84 silver, if you have an 83, you're out of luck. So if you don't have the squigglies, this is the squiggly. This is the notation that you use. This will calculate the definite integral of a function for you. Okay, so let's suppose we go back to the first problem that we did. The first problem was the integral, help me out, from 0 to 3 of x cubed. 0 to 3 of x cubed dx. X cubed is f of x. X is always going to be x. You just literally type in x. A is the lower limit of integration, and b is the upper limit of integration. If you have the squiggly mark on your calculator, you're just going to literally fill in everything that you have here. Put a 0 there, put a 3 there, put x cubed there, and put an x for dx. If you don't have the squiggly mark, then you've got to follow this notation. fn int, type in x cubed, comma, x, comma, 0, comma, 3, close parentheses. And by the way, the comma has its own button. It's above the 7.
Wait, say that one more time. So after that is.
So you would type into your calculator, fn int would pop up automatically. Then you would type x cubed, comma, x, comma, 0, comma, 3.
So it's not just from.
Do it and check to make sure you get the correct answer. What was the answer, 14?
25. So it's the 81 over 4.
Oh, 81 over 4. Okay, you did the second one.
Do you have to type in commas?
Yes, you need the commas, huh? Anytime you have a definite integral on the AP test, and AP test not necessarily my test, you'll be expected to use fn int. You need to know how to use this, because they're going to give you functions which you either can't find the antiderivative of, or it's going to be so nasty you'll scratch your eyes out trying to do it. Okay. So you need to learn this technique, just like the n derived that we talked about when we were doing derivatives. Okay? Day 62 will be due on Monday, because tomorrow is the quiz and it'll take most, if not all, of the period. On Monday, we'll start by going over this homework, which should just be mechanical calculations for you. You do have another assignment tomorrow night, which again will be due, so we're spending 3 days in 4-3. And then on Monday, we'll finish up with the second fundamental theorem of calculus. You might get some problems on tomorrow night's homework that you can't do because there's an overlap with the second fundamental theorem of calculus. So if it doesn't make any sense, skip it, but you should be able to knock out most of that day from tomorrow. Rosie?
Word for the class.
Day 62 and day 63 are due one day.
Correct.
Technically, yeah.
We are.
Clear reading.
Yes.
Yes.
Let's go to work.
We have to be able to